All right, for part C, we're asked to show that as u approaches these values where it's not smooth, that these vectors converge to what they should. Okay, so we're parameterizing a sphere, and the normal at the north pole, we want it to should be positive k hat. The normal at the south pole should be negative k hat. So I just copied down what we had: RU cross RV, r squared sine squared u cosine v, r squared sine squared u sine v, r squared sine u cosine u, and the magnitude of that we had is r squared sine u, which should look familiar. Rho squared sine phi, anyone? Anyway, if you go ahead and do this division, as long as sine of u isn't 0, we see we have common factors all over the place. The r squares cancel. One of the factors of sine u cancels, and I'm left with sine u cosine v, and I'm left with sine u sine v, and I'm left with cosine u. Alright, so as u goes to 0 from the right, and I take this limit, I do have a vector 0 over a number 0, so that's an indeterminate form. Okay, but that indeterminate form comes out in the wash because the zeros cancel out. And I'm going to be looking at this limit then, all right, because I'm taking the limit component-wise. And what's this limit going to go to? 0, 0, cosine of 0 is 1. And as u goes to pi from the left, I'm going to get a 0, 0, negative 1. And that's exactly what I need. So even though the surface isn't technically smooth, at those endpoints, the outward normal is converging to what it should be. And that means it's okay then to go ahead and do the flux on it. Okay, part D now. We're given an inverse square field F. Remember why it's called an inverse square field. If I take the magnitude of this, it's going to be 1 over x squared plus y squared plus z squared squared. So it's 1 over the distance from the origin. So that's why it's called that. Anyway, this is the field, and we're asked to find the outward flux of F across S, and this is Gauss's law. So outward flux is computed with the surface integral. I'm going to take F dot the outward normal ds. Now we've already shown in the last part that the outward normal I can get using RU cross RV. So really this boils down to integrating over the region R determined by those variables, f of uv dot the vector RU cross RV, which we've already computed, dA. So the only thing we have left to compute is what that is. Alright, so how do we do that? F of uv. Well, we go back to our substitutions. That's going to be x. That's going to be y. That's going to be z. Now, from before, we know that x squared plus y squared plus z squared is going to be r squared. That was the very first thing we did. So the denominator there is going to be r squared to the 3 halves. The numerators are going to vary depending on x, y, and z. So negative kx is going to be negative k r sine u cosine v. And on the bottom then we have r squared to the 3 halves power. Negative ky is negative k times r sine u sine v. And this is over r squared to the 3 halves power minus kz and I get that. Now since r is positive, I can simplify this. The r squared and the square root there cancel each other out, give me r cubed. And so I have negative k sine u cosine v over r squared minus k sine u sine v over r squared minus k cosine u over r squared. Alright, so that's f of uv. Now I need to take the dot product with RU cross RV, and that's going to be my integrand. Okay, so we need f of uv dot ru cross rv, so that's what we have there from before, and we'll do the dot product. I take this times that, the r squares canceled, I get a negative k, sine cubed u, cosine squared v, minus another k, the r squares cancel, I get a sine cubed u, sine squared v, so there's Pythagorean magic waiting to happen for us, minus k cosine squared u. Let's see, these two terms, cosine squared u, sine squared u, I have the exact same coefficient, so Pythagorean magic happens. I get negative k sine cubed u minus k cosine squared u. Excuse me. This is cosine squared u sine u. So there's a sine u there I forgot about, which makes all the difference in the world. I can factor out the negative k sine u and look at what's left. I get a sine squared u plus cosine squared u. And so I get negative k sine u. So the integrand of the flux integral is negative k sine u. So my outward flux, double integral over the surface S, f dot the outward normal ds. Parametrically, I'm going to do a double integral over the region R, f of uv dot ru cross rv dA. So this is double integral over R of negative k sine u dA. All right, now what's the region R I'm integrating over? When I go back up, here are my parameters for u and v. So my region R in the uv plane, u goes from 0 to pi, v goes from 0 to 2 pi. I get this rectangular region, so the order of integration really doesn't matter. I'll go from 0 to 2 pi, 0 to pi, negative k sine u du dv. I get the integral from 0 to 2 pi. I get k cosine u. U goes from 0 to pi dv. Cosine of pi is negative 1 minus cosine of 0 is negative 2. So negative 2k dv, and I get negative 4 pi k. So here's what Gauss's law says. If you have an inverse square field like this, okay, and you want the flux across the sphere of radius r, the flux is always the same. It's always negative 4 pi k, whatever that k happens to be. So if you think about it, what's happening geometrically is you have an inverse square field, which means it's weakening at a factor of 1 over the distance from the origin squared. So think of that as 1 over big R squared is how that field is weakening. Now, if you look at a surface, right, look at the sphere, the surface area of the sphere is increasing at a rate of big R squared, right? The surface area of a sphere is 4 pi R squared. So you can think in a way that the weakening of the field by a factor of 1 over R squared is offset by the surface area of the sphere increasing at a rate of R squared. And so the flux across the greater area is exactly offset by the because it's a further distance away from the origin. That'll do it for checkpoint quiz 23.